Alright, so we stop here in the compiler turns this line of code into assembly. So here is the program code which might look like something like this in x86 assembly. Use obj dump on Linux or otool on Mac to disassemble it. So you can actually use something command from Linux and Mac to disassemble this via its compiler. So this is the how the code looks like. 128 move L 0x0 percentage EVX etc. So there's a 3000 stock, a process and its address space, etc. This code snippet is relatively straightforward. It pressures that the address of X has been placed in the register EBX and then loads the value of that address into the generated general purpose register EAX using the MOVL instruction for long word move. Again, this code snippet is relatively straightforward. It presumes that the address of X has been placed in the register EBX. So here, load 0 plus EBX into EAX. And then this is where you add 3 to EAX register in 132 address space. And then loads the value at that address into the general purpose register EAX using the MOVL instruction for long word move. The next instruction adds 3 to EAX, and the final instruction stores the value in EAX back into memory at that same location. So here it adds 3 and then here it moves back into memory at that same location. So the next or the last instruction, the final instruction stores the value in EAX back into memory at that same location. So this same EAX that we have, since we added 3, we move it back that. So that's what the code does. In figure 15.1, observe how both the code and data are laid out in the process address space. The 3 instruction code sequence is located at address 128. The 3 instruction are located in address space 128 in the code section near the top. And the value of the variable X at address 15 kilobytes in the stock near the bottom. So in figure 15.1, observe how both the code and data are laid out in the process address space. The 3 instruction code sequence is located at address 128 in the code section near at the top. So the 3-step instruction, which is the int this void func int x equals to 3 and int x plus 3. So this int x equals to 3000 are loaded here in 128 and most of those initial instruction. And the value of the variable x at address 15 kilobyte in the stock near the bottom here. In the figure, the initial value of x is 3000 as shown in its location on the stock. When this instruction runs from the So as shown in this location and stock, the initial value is 3000. When this instruction run from the perspective of the process, the following memory accesses takes place. So again, it's worth emphasizing it in the memory's perspective, okay? It's not in another perspective, just like a network, but we're talking about in one perspective. So here it is, fetch instruction at address 128. Execute this instruction, load from address 15 kilobytes. So we will need to load that from 15 kilobytes because that's where our code lies. So here is the 15 kilobytes. Fetch instruction at address 132. So here we have additional 3. So first we load that, we execute that instruction, the int x equals to 3000 here, and then fetch instruction first at 132. So notice before we execute, we fetch the instruction first and then execute this instruction, no memory reference. So we add the +3 because that's the instruction at 132. Fetch the instruction at 135. So here's the 135. Execute this instruction, store to address 15 kilobytes. So we execute the instruction for 135, which is the exit, and then we fetch that first and then execute it and store that to 15 kilobytes as well, the same as the stock. From the program's perspective, its address space starts at 0 and grows to a maximum of 16 kilobytes. All memory references it generates should be within these bounds. However, to virtualize memory, the OS wants to place the process somewhere else in physical memory, not necessarily at address 0. Thus, we have the problem: how can we relocate this process in memory in a way that is transparent to the process? How can we provide illusion of virtual address space starting at 0 when in reality the address space is located at some other physical address? So that's our crux. So here, operating system, we have this in 32 kilobytes, the code and the heap, not allocated stock, etc. Physical memory with a single relocated process. So though we have here a process that starts at 0, how do we make an illusion that allows it to think that it still have that structure? Because again, the OS needs to have that first code in the physical memory, because that's the underlying manager of all the software. We will gonna answer that all throughout of this chapter. So dynamic hardware-based relocation. To gain some understanding of hardware-based translation, we'll first discuss its first incarnation. Introduced in the first time-sharing machines of the late 1950s, is a simple idea referred to as base and bounds. So to be able to understand how we actually translate it into hardware, we need to discuss the incarnation. So it started with the time sharing after the multi-programming in around 1950s, and a simple idea is a base and bounds. The technique is also referred to as dynamic relocation. We'll use both terms interchangeably. Specifically, we'll need two hardware registers within each CPU. One is called the base register and the other the bounds, sometimes called a limit register. So there is a base, the starting, and the bound, which is the limit of that physical memory size. This base and bound pair is going to allow us to place the address space anywhere we'd like in physical memory. So this mark from the hardware, with the help of the hardware, allowing us to track the start and the limit, allow us to place the address space of the process anywhere we'd like in physical memory, and do so while ensuring that the process can only access its own address. In the setup, each program is written and compiled as if it is loaded at address 0. So that's how we initially, or the first version of making it the OS thinks, or the process thinks that it starts from 0. In the setup, each program is written and compiled as if it's loaded at address 0. So it's written and compiled as if that way. However, when a program starts running, the OS decides where in physical memory it should be loaded. And sets the base register to that value. So when the program runs, or if it becomes a process, the OS decides where in physical memory it should be loaded and sets the base register to that value. So the OS are the one deciding, with the help of the hardware, where is the base register. In this setup, each program is written and compiled as if it's loaded at address 0. However, when a program starts running, the OS decides where in the physical memory should be loaded, and the base so in the example above, the OS decides to load the process at physical address 32 kilobytes, and thus sets the base register to this value. So as you can see, code the base it start at 32 kilobytes in the actual physical memory. So aside software-based relocation, in the early days, before hardware support arose, some systems perform a crude form of relocation purely via software methods. So instead of having a hardware support, OS having a hardware support, these relocation to physical memory are done purely by software methods, or by the functions we create on our code. The basic technique is referred to as static relocation, in which a piece of software known as the loader takes an executable that is about to be run and rewrites its address to the desired offset in physical memory. So you can think of that executable as the code that is about to be run. So that code will be executed, or will be rewritten by this static relocation, and it will rewrite its address to the desired offset in physical memory. For example, if an instruction was a load from address 1000 into a register, like move L 1000 or %EAX, the one we see earlier in 128, 132, and 135. So if that an instruction was a load from address 1000 into a register, move L 1000 %EAX, and the address space of the program was loaded starting at address 3000 and not 0 as the program thinks, the loader would rewrite the instruction to offset each address by 3000. So this loader will offset or rewrite the instruction to offset each by 3000. Move L 4000 from 1000. In this way, a simple static relocation of the process address space is achieved. So from that virtual, it became 4000 %EAX in the actual physical memory. However, static relocation has numerous problems. First and most importantly, it does not provide protection, as processes can generate bad addresses and thus illegally access other process or even OS memory. So these still have that initial problem with their OS, with the interrupt in which other process could take over other process, and the system call which the process could take over the OS. In general, hardware support is likely needed for true protection. Another negative is that once placed, it is difficult to later relocate an address space to another location. So once you are able to place that in, let's say you want to take that process from a different part of memory, it's difficult to do so. So those are the weakness of that. Interesting things start to happen when the process is running. Now, when any memory reference is generated by the process, it is translated by the processor in the following manner. So when a process suddenly call this or generate a memory reference such as virtual address, the processor are actually converting that using this formula: virtual address provided by the process plus the base register. Each memory reference generated by the process is a virtual address. So each memory reference or that memory reference is actually generated by the process is a virtual address. The hardware in turn adds the contents of the base register to this address, and the result is a physical address that can be issued to the memory system. So that physical address will be then returned to the process to be able to consume by the process. So that came from memory reference. So again, it's the hardware that does that, that adds that contents of that virtual address to its base register, because we still have this architecture of one base register and one bound register that allows us to control this memory. To understand this better, let's trace through what happens when a single instruction is executed. Specifically, let's look at one instruction from our earlier example. So here, 128 move L 0x0 percentage EBX comma percentage EBX. The program counter is set to 128. So these are the first instruction that we have in our program code. The program counter is set to 128. So initially, the program counter is set to 128. When the hardware needs to fetch this instruction, it first add the value to the base register value of 32 kilobytes. So here's what it looks like to get a physical address of 32896. So since that code, the program code starts from 128, and the code in the actual physical memory starts at 32 kilobytes, we just need to add that from 32768, which is the actual byte number, plus that 128. So this 128 is actually measured in bytes. So figure 15.2, physical memory with a single relocated process. So here's the relocated process code, and then we have stock allocated but not in use. As you can see, we have some allocated space but not in use. The reason for that is that, again, the stock will go up if it needs be by the code, and the heap will go down if it's need be by the programmer. The hardware then fetches the instruction from that physical address. So the hardware then fetches or load the instruction before it execute on that address, because again, you execute the processor execute its instruction, or that instruction provided by the code, on the physical memory address. Next, the processor begins executing the instruction. At some point, the process then issues the load from virtual address 15 kilobytes, which the process takes and again adds to the base register 32 kilobytes. So after it executes that 128, we have another instruction, where is that here 132, right? Int x plus is equals to 3000. So the OS will so at some point the process then issues the load from virtual address 15 kilobytes, which the process takes and again adds to the register 32 kilobyte, getting the final physical address of 47 kilobytes. So where's the 47 kilobyte? Here on the stack, and thus the desired contents. So it loads the instruction of that and then execute again at the stock, because that's where the stock is. Again, the stock is size 2 kilobytes. So I think 14 kilobytes, 15, 16. Yeah, it's 2 kilobytes the stock. So since it's 15 kilobytes, we just need to add that instruction to that 32 kilobytes with 132. So 15 kilobytes rather. 32 plus 15 equals to 14 kilobytes and the desired contents in the actual physical memory. Tip: hardware-based dynamic relocation. With dynamic relocation, a little hardware goes a long way. Namely, a base register is used to transform virtual addresses generated by the program into physical addresses. A bounds or limit register ensures that such addresses are within the confines of the address space. Together, they provide a simple and efficient virtualization of memory. So this dynamic relocation is just one way for us to virtualize memory. So these are one of the pioneers in which we manage memory, like providing virtual memory for each process, because that is required by this interactive time sharing multi-process application. Transforming a virtual address into physical address is exactly the technique we refer to as address translation. So the one that we created earlier using the processor is actually what we call address translation. That is, the hardware takes a virtual address, the process thinks it is referencing, and transform it into physical address, which is where the data actually reside. Not just so once it transforms it to physical address where the data resides or the memory address resides, it loads that instruction and execute it. Because this relocation of the address happens at runtime, and because we can move address spaces even after the process has started running, the technique is often referred to as dynamic relocation. So the reason it's called dynamic relocation is because it's happening at runtime using hardware. Actually, hardware are the one that actually locate the physical address, and we can actually change the position during, even if the after the process has started running. Now you might be asking what happened to that bounds limit registers. After all, this is the base and bounds approach. Indeed, it is, as you might have guessed. The bounds register is there to help with protection. So we discuss only the base, right? We The processor determine the physical address using the base. So what do we do with the bound if it's included in the concept of dynamic relocation? Indeed, it is. As you might have guessed, the bounds register is there to help with protection. Specifically, the processor will check that the memory reference is within the bounds to make sure it is legal. So the use case for that is to make sure that we're not accessing over what is allowed on the memory. In the simple example above, the bounds register would always be set to 16 kilobytes. So here, so we have the code. So there's a limit of 16 kilobytes for that process. Therefore, any instruction that go over that would not be executed and will be rejected by the OS. If a process generates a virtual address that is greater than or equal to the bounds, or one that is negative, the CPU will raise an exception. So not just equal, so not just greater than, but also equal to the bounds, because if it's equal to the bounds, it means that we also hit our limit. Or one that is negative, because we don't have negative numbers in memory. The CPU will raise an exception and the process will likely be terminated. The point of the bounds is thus to make sure that all addresses generated by the process are legal within the bounds of the process, as you might have guessed. We should note that the base and bounds registers are hardware structures kept on the chip, one pair per CPU. So the reason why we're able to do this is because of the inherent base and bound register each or per pair of CPU. So this CPU was created before that allow us to generate this. So remember the Moore's law, where CPU kept advancing. So this is one of the innovation they have created to enable this dynamic relocation. Sometimes people call the part of the processor that helps with address translation the memory management unit, or MMU. So this is what people think when they mention MMU. As we develop more sophisticated memory management techniques, we will be adding more circuitry to the MMU. So this pair of base and bound register of the per pair of the CPU, along with the translation mechanism using virtual address plus base register and using bound to raise an exemption, is what people call MMU. But there's actually more into it, as we will later see as we get into more sophisticated details of memory management. A small aside about bound registers, which can be defined in one of two ways. In one way, as above, it holds the size of the address space, and thus the hardware checks the virtual address against it. So the bound registers can be defined in two ways. In one way, as above, it holds the size of the address space. So the size, such as the 16 kilobytes of the process, and thus the hardware checks the virtual address against it. So the hardware just needs to compare if it's equal or more than that allocated. After all, it will add the base. After all, the processor will add the base, so it needs to be equal to that or not go over the limit allocated to that process. In the second way, it holds the physical address of the end of the address base, and thus the hardware first adds the base and then make sure the address is within bounds. In this again, in the second way, it holds the physical address of the end of the address space. And thus the hardware first add the base and then make sure the address is within bounds. So it also have the last or the bound of the physical address or the physical memory. Therefore, it will just check that against there. If it's more than, for example, your memory, like a 16 gig, therefore it will reject it. Both methods are logically equivalent. For simplicity, we'll assume the former method, which is the process size instead of the, or checking it against the process size instead of the memory. To understand address translation via base and bounds in more detail, let's look at an example. Imagine a process with an address space of size 4 kilobytes. Yes, unrealistically small, has been loaded at physical address 16 kilobytes. Here are the results of the number of address translations. Virtual address 0, physical address 16 kilobytes, 1 kilobyte 17. So a process with an address space 4 kilobytes, yes, unrealistically small, has been loaded at physical address 16 kilobytes. Here are the results of a number of address translations. So virtual address 0, you start at 16 kilobytes, 1 kilobytes to 17 kilobytes, 3000 is equals to 19,384 kilobytes of physical address. Once you get to 4,400 fault, it's out of bounds. As you can see from the example, it's easy for you to simply add the base address to the virtual address, which can rightly be viewed as an offset into the address space to get the resulting physical address. Again, as you can see from the example, it's easy for you to simply add the base address to the virtual address, which can rightly be viewed as an offset into the address space to get the resulting physical address. Only if the virtual address is too big or negative will the result be a fault. So only if it's too big or negative, but if it's enough for that physical address, then it won't cause an exception, causing an exception to be raised. So that 4 kilobyte could be out of bound in this 16 kilobyte physical address if you just focus on the base case, because you will then end up starting at the you will end up starting at the 16 kilobytes, which is the end of that physical address space. Now, hardware support summary. So we will start this with this representation, hardware requirements, and notes. So to support this dynamic reallocation and this type of serving the memory to achieve that protection and flexibility, we have privilege mode. So in here, it's needed to prevent user mode processes from executing privilege operations, just like in an OS, right? So you have still this kind of like limited direct execution. Base and bound registers need a pair of registers per CPU to support address translation and bound checks. So just like what I mentioned, that this pair of CPU must have this inherent capability to handle base and bound registers, ability to translate virtual addresses and check if within bounds. So it also has need to have an ability to translate virtual addresses and check if within bounds. Circuitry to do translation and check limits, in this case quite simple. So this processor must also be able to accept or compile that virtual address requested by the process and then translate it to an actual physical address. So we will gonna further debunk or provide those information. So it's a circuitry to do the translation and check limits. So basically it translate that and then check the base and bound. In this case it's quite simple, right? Because we just use base and bound to do that. Privilege instruction to update base and bounds. OS must be able to set these values before letting a user program run. So the OS must be able to set this base and bound. So allocate this base and bound first to the process before the process could choose that. Because imagine if the process could set its base and bound and then not having the OS control that, it will cause disaster. Privilege instructions to register exception handlers. OS must be able to tell hardware what code to run if exception occurs. An OS must be able to tell hardware what code to run if exception occurs. Privilege instruction to register exception handler. So it also must provide this exception handler, kind of like in the trap table of system handler and the interrupt. So the OS must be able to tell or register that to the hardware. So basically we will gonna register that at the beginning of the boot as well. Ability to raise exception when processes try to access privileged instruction or out of bound memory. So basically we'll gonna OS will gonna handle that using the trap table. So a single bit perhaps stored in some kind of processor status word indicates which mode the CPU is currently running in. So a single bit perhaps stored in some kind of processor status word will indicate which mode the CPU is currently running in. Upon certain special occasion like system call or some other kind of exception or interrupt, the CPU switches mode. The hardware must also provide the base and bounds registers themselves. So the hardware must also provide the base and bounds registers themselves. So again, a single bit perhaps stored in some kind of processor. So that bit are stored in some kind of processor status word will indicate which mode the CPU is currently running in, whether it's privilege mode or user mode. Upon certain special occasion like system call or some other kind of exception, the CPU switches mode, kind of like when it's in a privilege mode, then the kernel knows to convert that virtual address to physical address. The hardware must also provide the base and bound registers themselves. So the hardware again needs to provide that. Each CPU does has an additional of a pair of registers, part of the memory management unit of the CPU. So this base and bound, commonly thought of MMU, must be part, or it's actually part of the pair of CPU. When a user program is running, the hardware will translate each address by adding the base value to the virtual address generated by the user program. The hardware must also be able to check whether the address is valid, which is accomplished by using the bounce register and some circuitry within the CPU. So aside from bounce, there's some circuitry there, which is more sophisticated, that allows us to reject if it is out of bounds. The hardware should provide special instruction to modify the base and bounce registers, allowing the OS to change them when different processes run. Again, the hardware should provide special instructions to modify the base and bounce registers. So it should provide this system call that allows the process to modify that base and bounce registers, allowing the OS to change them when different processes run. So it should provide the OS as well to change them depending on the processes that is needing it. These instructions are privileged. Only in kernel or privileged mode can the registers be modified. So just like a system call, the invoking or changing or modifying this base and bound register for dynamic relocation strategy for memory are also only allowed in privileged mode. Imagine the havoc a user process could wreak if it could arbitrarily change the base register while running. Finally, the CPU must be able to generate exceptions in situation where a user program tries to access memory illegally. So the CPU again must be able to generate exceptions in situation where a user program tries to access memory illegally with an address that is out of bounds. In this case, the CPU should stop executing the user program and arrange for the OS out of bounds exception handler to run. So the CPU itself must detect if the process are requesting an out of bound, and then must trigger the OS to now invoke that exception handle for that out of bound request. The OS handler can then figure out how to react, in this case likely terminating the process. So that OS handler must terminate the process. Similarly, if a user program tries to change the values of the privilege base and bound registers, the CPU should raise an exemption as well and run the try to execute a privilege mode operations, or having the OS invoke that error, try to execute a privilege operation while in user mode handler. The CPU also must provide a method to perform it, to inform it of the location of these handlers. A few more privilege instructions are thus needed. So there's also so the design of this also must require an instruction provided to inform of the location of these handlers that the CPU, the OS could invoke. Remember, at boot time, we register that entrap handler, and the hardware remember that. So the OS will likely invoke that in case there's that exception. Operating system issues. So we're done with the summary of hardware support that needed, or the low-level mechanism needed for us to process this base and bound dynamic relocation design. of virtual memory will now go on the operating system's issues point of view. Now, just as hardware provides features to support dynamic relocation, the OS now has new issues if it must handle. The combination of hardware support and OS management lets the implementation of a simple virtual memory. So because of that hardware support needed for that dynamic reallocation and the OS management that existing in the system leads to the implementation of a simple virtual memory. Specifically, there are a few critical junctures where the OS must get involved to implement our base and bounds version of virtual memory. So there's a critical step where the OS needs to take over to manage the base and bounds of that dynamic relocation. First, the OS must take action when a process is created, finding space for its address space in memory. Fortunately, given our assumptions that each process space is smaller than the size of a physical memory and the same size, this is quite easy for the OS. So the way we do this first is that once it's created, we need to find finding space for its address space in memory. So the OS must take action to find that the physical memory available for this process. So it's easy to do that because the OS knows the physical size of the memory and the process, because it's the one that's allocated it can simply view physical memory as an array of slots and track whether each one is free or in use. So if you want to know the details of how it actually view physical memory track how many memories available, physical memories, it can simply view that as an array of slots and track whether each one is free or in use. When a process is created, the OS will have to search a data structure. So it does this in details by searching a data structure, often called a free list, to find room for the new address space and then mark it used. With the variable size address spaces, life is more complicated, but we will leave that concern for future chapters. So it uses an algorithm that allows it to search for the data structure called free list. So this is a simple way that OS manage dynamic relocation of this virtual memory, because it has a fixed size of the address space available in this physical memory. It divides the space for processes in a fixed way, but as we will later learn in the next chapters, there is more complicated way to handle the memory with just a variable size memory. So here are the representation, kind of like the same as with the hardware we created before. So OS requirements for memory management, it is needed to allocate memory for new processes. So memory management, you can think of that as like the malloc, right? Malloc library. So it can reclaim memory from terminated processes. So like the stock, it can it's automatically managed, but the process, there's the process when killed, when executed properly, the OS automatically distribute that to other process. So that's the memory management that we're talking about here. Generally manage memory via free list. So since again we're talking about fixed size, we use the free list data structure. Base and bounds managements, it also must set base or bounds properly upon context switch. So the OS must also be there in this critical switch, kind of like the context switch we discussed in the previous video. It allows the interrupt, right? So the OS also must track those save and restore registers, etc. Exception handling as well. So it needs to be in this critical path or critical points. Code to run when exception arise. Likely action 2 is to terminate offending process. So here's dynamic relocation. Operating system responsibilities for dynamic relocation. So in page 15.2, you can see the OS using the first lot of memory for itself, that it has relocated the process for the example above into the starting at physical memory address 32 kilobytes. So the other two slots are free, 16 kilobytes 32 to 32 kilobytes and 48 kilobytes to 64 kilobytes. Thus, the free list should consist of these two entries. So the free list, the data structure for dynamic relocation should contain this not in use part in the physical memory. Also, as you can see, since it's dynamic relocation, it doesn't actually put that process that seemed to be starting at 0 kilobytes in a physical memory. It actually puts where it requested the virtual address, such as the code in 128 plus 32,000 kilobyte, something like 32,768. So this is where it actually does that. Second, the OS must do some work where a process is terminated. When it exits gracefully or forcefully killed because it misbehaved. Again, second, the OS must do some work when process is terminated. So this is where the getting the free space and allocating it to another process when it exits gracefully or forcefully killed because it requested more memory or misbehaved, reclaiming all of its memory for use in other processes or the OS. So that's the second responsibility of the OS. Kind of like if the hardware has that responsibility to have base and bound register, the OS must also have this responsibility to execute that in the trap handler that it registered and then free that and then use that on other processes. Upon termination of a process, the OS puts its memory back on the free list and cleans up any associated data structures as need be. So it actually cleared that in the free list and then clear it any associated data structure as need be. Third, the OS must also perform a few additional steps when a context switch occurs. So for context switch, this is also a responsibility of the OS. There's only one base and bound register pair on each CPU. After all, their values differ for each running program, as each program is loaded at different physical address in memory. Again, there is only one base and bounds register pair on each CPU. After all, their values differ to each running program. So their values for each running program, just like here, is different, right? So you can put a program here, so the base and bound are different. So as each program is loaded a different physical address in memory, thus the OS must save and restore the base and bounds pair when it switches between process. So this is what I'm saying, the save and restore register, where in the previous video we explicitly save and restore using the OS, the in the process structure, the context, or the base and bound register of that process. So it's the same here. This is the same with dynamic relocation. Specifically, when the OS decides to stop running a process, it must save the values of the base and bound registers to memory in some per process structure. Right? So this is what I'm saying, the proc structure we have discussed in the previous video, such as the process structure or process control block, which we have discussed deeply in the previous video. Similarly, when the OS resumes running process or runs it the first time, it must set the values of the base and bounds on the CPU to the correct values for this process. So when it resume, it shall resume that previous save base and bound register that it explicitly saved to its process control block. So kind of like way of tracking that process where it left off in the process control block, kind of like in the previous video. So it's the same. It's actually the same. So whether it's starting that for the first time or resuming it, it must save it explicitly to track it on the system whenever it does this context switch. We should note that when a process is stopped not running, it is possible for the OS to move an address space from one location in memory to another rather easily. To move a process address space, the OS first deschedules the process, then the OS copies the address space from the current location to the new location. So this is another power of the OS that it must be able to easily do. When the process is stopped, it can copy that data and then paste it to a new location in the actual physical memory. Finally, the OS updates the save base register in the process structure to point to the new location. So that previously saved base and bound for this stop process could be saved onto that new location in memory. When the process is resumed, its new base register is restored and it's begin running again, oblivious that its instruction and data are now in a completely new spot in memory. Fourth, the OS must provide exception handlers or functions to be called. As discussed above, the OS installed these handlers at boot time via privilege instructions, like what I've said. For example, if a process tries to access memory outside its bounds, the CPU will raise an exception. The OS must be prepared to take an action with such an exception arises. The common reaction of the OS will be one of hostility. It will likely terminate the offending process. So here is how we register that at the boot time. So initialize trap table, the OS, then remember addresses of system call handler, timer handler, illegal memory access handler, illegal instruction handler as well. And then the OS start interrupt timer. So there will be an interrupt, every some seconds, some milliseconds, and then the start timer of the hardware will start and then interrupt after XMS, and then it will initialize process table, initialize free list. So that process table is what allow us to keep track of the processes and then the free list and the available memory for that processes. So now it's more sophisticated, right? Before we only have that process table, we don't have this free list. So here is the diagram including a mouse click. So how do we actually see the mouse click here in this representation? So to start process A, we allocate entry first in process table. Allocate memory for that process, we set base and bound registers, and then return from trap into A. Then we get into the hardware, to the privilege mode, restore registers of A, so it restores the register it saved from A. Move to user mode, so if it didn't run the process A before, therefore it will start it as new. It will therefore save that register for a new process A. It will move to user mode for the program to directly take over of this process. It will jump to A's initial program counter again, to that initial program counter, to that main where the program starts, and then process A runs. So if it is a register, if it just resume, it will resume to that previous base and bound of the process counter. So process A runs, it fetch instruction first, provided by that register, save in the hardware, execute instruction, and then A runs. So note, in real hardware, interrupts are only handled between instructions. So the interrupts are actually being handled between instructions in real hardware, in real operating system. Basically, that purpose of that interrupt is to actually switch between processes. So let's say the one process are doing IO, you can switch to another process while the other are doing that based on the interrupt timetable. We're going to discuss that further. So the CPU finishes one instruction of A, then checks if an interrupt is pending. So it finished first the instruction of A and check if there's an interrupt pending that needs to be done after that instruction of A is complete. So if the timer interrupt is pending, oh my god, what's that? So if the timer interrupt is pending, timer interrupt, move to kernel. So after the process RAM, we use the timer interrupt, we move to kernel mode again, jump to timer handler, and then this OS will handle the timer. Decide to stop A, run B, call switch routine, it will save register and proc and the base and the bound register to proc process structure, and then it will restore register B base and bounds process structure, and then return from trap into B. Or if the mouse interrupt is pending, mouse interrupt, move to kernel mode, jump to mouse handler. So the OS, so notice when we there's a mouse interrupt pending, like when you click another applications between processes, such as clicking Notepad and Microsoft Word, it will tap into the OS first. It will be handled by the OS, or handled via its system call, handle mouse input, process mouse click, post event to process B's queue. Scheduler may decide to stop A, run B. So it will post an event to process B's queue. So it will be queue on the system, and the scheduler, which is the algorithm we discussed in the previous video, will decide to stop A and then now run B, depending. But most operating system could run the, for example, YouTube on the background while you're doing the OneNote, for example here. But sometimes if the processor cannot do that, not enough processing capacity, therefore you have to stop the YouTube. So this is how it does that. Then same switch routine as above, which is here, context switching for different processes, and then it will move to hardware. It will restore register of B. The hardware will register now the V. It will move to user mode, and then the hardware will now jumps to the B's program counter in the memory, and then it will load that instruction and then execute it and then handle the click event process by the user for the process B. Now figure 15.5, 15.6, page 12 illustrate how much of the hardware or OS interaction in a timeline. The first figure shows what the OS does at boot time to ready the machine for use. The second shows what happens when a process A starts running. Notes how its memory translation are handled by the hardware with no OS intervention. So here, as you can see, the memory translation are handled by the hardware with no OS intervention. Let's see that, just a moment. So this is the original diagram, guys. So here, note how its memory translations are handled by the hardware with no OS intervention. So here, return from trap restores registers of A, move to user mode, jump to initial PC, process A run, fetch instruction. So after it fetch instruction, then it goes again to the hardware. It translates virtual addresses, perform fetch. So it doesn't have OS intervention here. And then the process execute instruction. If explicit load or store, ensure address is legal. Translate virtual address, perform load store if it's legal. Then A runs. And timer interrupt, move to kernel mode, jump to handler. Then handle timer decides stop A run because which routine saves register A to process structure including base and bound registers B from and then restores reg base and bound from block structure B, return from top into B, and then restores the hardware restores registers of B, move to user mode, jump to B's PC. Process B run, execute bad load. Load is out of bounds. So since it's out of bounds, move to kernel mode, jump to trap handler. So handle the OS will handle the trap, decide to kill process B. They allocate B's memory, free B's entry in process table. So that's how it looked like when we have out of bound requests for another process. So at some point, middle of second figure, a timer interrupt occurs and the OS switches to process B, which executes a bad load to an illegal memory address. At that, a timer interrupt occurs and the OS switches to process B, which execute a bad load to an illegal memory address. At that point, the OS must get involved, terminating the process and cleaning up by freeing B's memory and removing its entry from the process table. So again, a timer interrupt occurs and the OS switches to process B, which execute a bad load to an illegal memory address since it's out of bound. At that point, the OS must get involved, terminating the process and cleaning up by freeing base memory and removing its entry from the process table. As you can see from the figures, we are still following the basic approach of limited direct execution. In most cases, the OS just sets up the hardware appropriately and lets the process run directly on the CPU. Only when the process misbehaves does the OS have to become involved. So it's still a limited direct execution. That's why it has similarities from the previous video. But the difference is that the hardware took over the virtual address translation. It fetched first the instruction and then it converts that into virtual address where to execute, and then execute the process A, and then process A execute, and then back to the timer interrupt. What is that? If explicit load or store ensure address is legal, so that's part of the hardware kind of like if statement. Then A continues to run, time interrupt, move to kernel mode, jump to handler, and then handler timer decide to stop A, then run B, call switch routine, save register to proc structure, including base and bound, restores register B, and then we go back to the kernel, restore register B on the kernel, move to user mode, jump to base PC, process B run, it execute bound load. So now we actually are able to use the kernel out of bound. If else, then the OS will handle that trap. It will kill and free the base memory in a process table. So here's what it is. So that's what that means. As you can see from the figures, we're still following the basic approach of limited direct execution. In most cases, the OS just sets up the hardware appropriately and lets the process run directly on the CPU. Only when the process misbehaves does the OS have to become involved. So summary, in this chapter, we have extended the concept of limited direct execution with a specific mechanism used in virtual memory known as address translation. So now we are being more sophisticated on how we actually see how the modern operating system handles these processes. We added a mechanism to translate it. So with address translation, the OS can control each and every memory access from a process. Again, with the address translation, the OS can control each and every memory access from a process, ensuring the access stay within the bounds of address space. So that's actually how the operating system and hardware make sure that the processes has its virtual address space or private address space. Key to the efficiency of this technique is hardware support, which perform the translation quickly for each access, turning virtual addresses, the process view of memory, into physical one, the actual view. Then key to the efficiency of this technique is hardware support, which perform the translation quickly for each access. So it uses the base and bound pair of the CPU to translate that turning for each access, turning virtual addresses like the process view of memory into physical ones, the actual view, and then executed, and then having if else if it executed a valid load. All of this is performed in a way that is transparent to the process that has been relocated. So it is transparent because again we're using a limited direct execution where the program or the process are actually talking directly to the hardware. The process has no idea its memory references are being translated, making for a wonderful illusion. So again, all of this is performed in a way that is transparent to the process that has been relocated. So this process are actually transparent to the one has been relocated by the hardware, and the process has no idea its memory references are being translated into a virtual address, kind of like we saw earlier how the CPU translate that, fetch the instruction, translate it to virtual address, and execute the code, making for a wonderful illusion. We have also seen one particular form of virtualization known as base and bounds or dynamic relocation. So this is just another form of virtualizing memory, but there's much more as we will discuss in the future videos. Base and bounds virtualization is quite efficient as only a little more hardware logic is required to add the base register to the virtual address. So this base and bound type of virtualization is efficient as you only need base for the hardware of the CPU, which a lot of CPU have available today, to add the base register to the virtual address and check the address generated by the process in bounds. Base and bounds also offers protection. The OS and hardware combine to ensure no process can generate memory references outside its own address space. So the if-else of the hardware and the handler of the OS work together to make sure that the process doesn't actually access its out-of-bound limit. Protection is certainly one of the most important goals of the OS. Without it, the OS could not control the machine. If processes were free to override memory, they could easily do nasty things like override the trap table and take over the system. Unfortunately, this simple technique of dynamic relocation have its inefficiencies. For example, as you can see in figure 5 here, the relocated process is using physical memory 32 to 48 kilobytes. However, because the process stack and heap are not too big, all of the space between two is simply wasted. So here, allocated but not used. So this type of waste is usually called internal fragmentation, as the space inside the allocated unit is not all used, like is fragmented and thus wasted. In our current approach, although there might be enough physical memory for more processes, we are currently restricted to placing an address space in a fixed size slot, and thus internal fragmentation can arise. So although there might be enough physical memory for more processes, this should not be used because we can only insert it here and here. A different solution might instead place a fixed size stack within the address space. So one solution could be putting a fixed size stack in the address space just below the code region. So here code, and then we have a stack here and a growing heap below that, and then the heap is the third. However, this limits flexibility by making recursion and deeply nested function calls challenging. So deeply nested like loop and deeply nested loop and recursion will be challenged to implement in that kind of structure of memory or virtual memory of the OS, and thus something we hope to avoid. Thus, we are going to need more sophisticated machinery to better utilize physical memory and avoid internal fragmentation. Our first attempt will be slight generalization of base and bounds, known as segmentation. So it's a slight generalization of the base and bound, which we will call segmentation. So it's another form again of virtualizing memory. So that's our next topic. So as you can imagine from 16.1, so here's segmentation. As you can imagine from figure 16.1, although the space between the stock and the heap is not being used by the process, it's still taking up physical memory when we relocate the entire address space somewhere in physical memory. Thus, the simple approach of using a base and bounds register pair to visualize memory is wasteful. It also makes it quite hard to run a program while the entire address space doesn't fit into memory. Thus, base and bounds is not as flexible as we would like. So as we can see, where's the 16.1? Yeah. So it's still taking up space even though it's not being used by heap and the stock and the process. So it's still taking up physical memory when we relocate the entire address space in the physical memory using that dynamic relocation. So we were able to provide this magnificent illusion, but it's not a memory efficient because there's that not allocated code. So the crux, so it also makes it quite hard to run a program when the entire address space doesn't fit into memory. Thus, base and bounds is not as flexible as we would like to. So the crux, how to support a large address space. How does we support a large address space with potentially a lot of free space between the stock and the heap? Note that in our examples, with tiny pretend address space, the waste doesn't seem too bad. Imagine, however, a 32-bit address space, 4 gig in size. A typical program will only use megabytes of memory, but still would demand that the entire address space be resident in memory. Again, how to support a large address space? How do we support a large address space with potentially a lot of free space between the stock and the heap? So how do we overcome this not allocated space? Note that in our example with tiny pretend address space, the waste doesn't seem too bad. Imagine, however, a 32-bit address space, 4 gig in size. A typical program will only use megabytes of memory, but still would demand that the entire address space would be resident in memory. So here, an example of that, an address space again. Segmentation. So a general base or bound approach. So to solve this problem, an idea was born, and it is called segmentation. It is quite an old idea, going at least as far back as the very early 1960s. The idea is simple. Instead of having just one base and bounds pair in our MMU, why not have base and bounds pair per logical segment of the address space? A segment is just a contiguous portion of the address space of a particular length. And in our canonical address space, we have 3 logically different segments: code, stock, and heap. What segmentation allows the OS to do is to place each one of those segments in different parts of physical memory, and thus avoid filling physical memory with unused virtual address space. So to avoid that unused virtual or filling the memory with unused virtual address space, we're gonna use a separate base and bounds for each we're gonna use a separate base and bounds for each logical segments, which is a contiguous portion of the address space of a particular length, such as the heap, the code, and the stock in our process. So let's look at an example. Assume we want to place the address space from figure 16.1, which is here at the top, into into a physical memory. With a base and bounds pair per segment, we can place each segment independently on physical memory. So if we separate this base and bound for this logical, we can have that separated in physical memory and still have this available for other processes. So for example, see figure 16.2. There you see 64 kilobyte in physical memory with those 3 segments in it. And 16 kilobytes reserved for the OS. As you can see in the diagram, only used memory is allocated space in physical memory. And thus, large address space with large amounts of unused address space, which we sometimes call sparse address spaces, can be accommodated. Again, as you can see in the diagram, only used memory is allocated space. Only used memory is allocated space in physical memory, and thus large address spaces with large amount of unused address space, which we sometimes call sparse address space, can be accommodated. So this 64 kilobytes has 3 segments, 16 kilobytes reserved for OS, this, and then this, and then this. So as you can see, we have code, heap, and the stock. It doesn't have those same structure as before, like code, heap, and then the stock at the bottom. So the hardware support in our MMU required to support segmentation is what you'd expect. In this case, set of 3 base and bound register pairs. So if the CPU earlier has only 1 base and bound register pair, now we need to upgrade the hardware as well. It needs to support 3 base and bound segment, which is for code, heap, and stock, or base and bound per pair of logical segment. So figure 6.3 below shows the registers values for the example above. Each bounds registers hold the size of a segment. So you can see from the figure that the code is placed at physical address 32 kilobytes and a size of 2 kilobytes, and the heap segment is placed at 34 kilobytes and has a size of 3 kilobytes. The size segment here is exactly the same as the bounds register introduced previously. So that size is actually how we measure the bounds of this. So just like what we did earlier with the physical memory, the bound could be the size of the process or the physical memory. Now, this size of this logical segment would be the new bound that we will introduce. So it tells the hardware exactly how many bytes are valid in this segment, and thus enable the hardware to determine when a program has made an illegal access outside of these bounds. Let's do an example translation using the address space in figure 16.1. Assume our reference is made to a virtual address 100, which is in the code segment, as you can see virtually in figure 16.1. Page 2. So here, when the reference takes place, say on an instruction fetch, so let's say just like before, when a reference takes place in instruction fetch, the CPU needs to do a virtual address translation. The hardware will add the base value to the offset into this segment, 100 in this case, to arrive at the desired physical address 100 plus 32 kilobytes or 32,868. It will then check the address is within bounds. 100 is less than 2 kilobytes. So it will add first, and then the hardware will do two things. It will add first to the 32,000, and then it will check if it's more than the size. So that's how it check the base and bounds. So again, it still use the basic principle of the base plus the virtual address. So the base is 32 kilobytes and the virtual address is 100. Find that it is and issue the reference to physical memory address 32868. So just like when the hardware are talking to the program earlier, when it convert the virtual address and then execute the instruction fetch to the program, this is what the hardware will do in this case. So here, placing segments in physical memory. So aside the segmentation fault, the term segmentation fault or violation arises from a memory access on a segmented machine to an illegal address. So that's what we call segmentation fault. When a process are trying to access memory that it's not, it's out of bound, or it doesn't have kernel mode access. Humorously, the term persists even on the machines with no support for segmentation at all, or not so humorously if you can't figure out why your code keeps faulting. So it's not funny anymore if you can figure out why your code keeps faulting. So now let's look at an address in the heap, virtual address 4200. Again, refer to figure 16.1, which is here. If we just add the virtual address 4200, so again, if a heap provides us a virtual address 4200, how do we actually measure that? If we just add the virtual address 4200 to the base of the heap, which in this case is actually 32, 33, 34 kilobytes, we get a physical address of 39,016, which is not the correct physical address. So what we need to first do is extract the offset into the heap, like which byte in this segment address refers to. So we need to first think which byte in that address or virtual physical memory address are we referring to, because the heap starts at virtual address 4 kilobytes or 4096. The offset of 4200 is actually 4200 minus 4096 or 104. Sorry, we're actually talking about here for 4 kilobytes to until 7 kilobytes of heap in figure 6.1. We're actually not talking, sorry, let me check this further. We then take this offset 104 and add it to the base register physical address. So in the heap or on the program code, the size of that is actually the 4200 minus 4096, because that's where the heaps start in the process, not in the physical memory, in the virtual memory. Then we add that to the actual base of the heap in virtual memory, which is added to base register physical address, which is 34K, to get desired 34920, which is still inbound because it's not out of bound. What if we try to refer to an illegal address, like a virtual address of 7 kilobytes or greater, which is beyond the end of the heap? You can imagine what will happen. The hardware detects that the address is out of bounds, trapped into the OS, likely leading to the termination of offending process. So because that's the normal behavior of the OS. It was designed like that to terminate those out-of-bound memory requests. And now you know the origin of the famous term that all C programmers turn to dread, the segmentation violation or segmentation fault. In our example above, we have 3 segments. Thus, we need 2 bits to accomplish our task. Again, in our example above, we have 3 segments. Thus, we need 2 bits to accomplish our task. If we use the top 2 bits of our 14-bit virtual address to select the segment, our virtual address looks like this. Where is that? I think this is where we stop, because let me check that. Yeah, I accidentally deleted it. Okay, so we shall remove that. Yeah, so which segments are we referring to? So the hardware uses segment registers during translation. How does it know the offset into a segment and to which segment and address refers? One common approach, sometimes referred to as an explicit approach, is to chop up the address space into segments based on the top few bits of the virtual address. This technique was used in the VAX or VMS system. In our example above, we have 3 segments, thus we need 2 bits to accomplish our task. If we use the top 2 bits of our 14-bit virtual address to select the segment, our virtual address looks like this. I think we'll have to continue with this. So again, let's try again, maybe until here. So the hardware uses segment register during translation. How does it know the offset into a segment? An address refers. One common approach, sometimes referred to as an explicit approach, is to chop up the address into segments based on the top few bits of the virtual address. So this is answering the question on how we can actually logically segment contiguous memory, such as heap, what do you call this, code, and the stock. So again, the hardware uses segment registers during translation. So that segment registers are doing this. How does it know the offset into a segment? and to which segment an address refers. So the offset, like the 4000 kilobytes minus somethings, or one common approach, sometimes referred to as an explicit approach, is to chop up the address space into segments based on the top few bits of virtual address. The technique was used in the VOX or VMS system. In our example above, we have 3 segments, thus we need 2 bits to accomplish our task. If we use the top 2 bits of our 14-bit virtual address to select the segment, so our visual address looks like this. So since we have 3 segments, we need 2 bits to accomplish our task. So if we use the top 2 bits of our 14-bit virtual address to select the segment, so this is the segment and then this is the offset, our virtual address will look like this. 01 segment, and this is the offset. So this is how you place the segment in virtual memory. So in our example, then if the 2 bits are 00, then the hardware knows the virtual address is the code segment. So there's like a pattern, and thus uses the code base and bounds pairs to relocate the address to the correct physical location. So this is how the hardware knows if it's a code segment, because it's the start, right? The code, the heap, and lastly the stock. So if the 2 bits are 01, the hardware knows the address is in the heap, because that's where the next part or the next segment after the code, and thus uses the heap, base, and bounds, and thus it will use now the heap, base, and bounds. So this is how we translate that offset number. And the what is the question earlier? So this is if the 2 bits are 01, the hardware knows the address is in the heap, and thus uses the heap, base, and bounds. Let's take our example heap virtual address from 4200 and translate it, just to make sure that this is clear. So the virtual address 4200 in binary form can be seen here. So this is how the heap will look like. So remember, the hardware help us in some way to save this, to get this pairs. But earlier we only discussed one pair, which is supported by the inherently by the CPU. But how does it actually support multiple segments, and how does it support segment register? So here is how it does that. So here 01, since it is a heap, as you can see from the picture, the top 2 bits 01 tell the hardware which segment we are referring to. The bottom 12 bits are the offset into the segment. So these are the offset into the segment: 000, 0110, and then 1000, or hex 0x068, or 104 in decimal. So that's actually the code we have previously, right? It's 104. Thus the hardware simply takes the first 2 bits to determine which segment register to use, and then takes the next 12 bits as the offset into the segment. So that's how it knows the offset. That's the value, which is 104. So by adding the base register to the offset, the hardware arrives at the final physical address. Note the offset uses the bounds to check 2. So it uses the offset to add that on the physical address to, by adding the base register to the offset, so it adds that to the base register of the now found heap using the 01. It now arrived at the final physical address. So that's how the hardware determined the logical segmentation of the segment register. Note the offset eases the bound checks to. We can simply check if the offset is less than the bounds. So this offset also eases the bounds as well, because we just need to check if the offset is less than the bounds. If not, then the address is illegal. Therefore, the OS or the CPU can simply reject that. Thus, if base and bounds were arrays, so if we're using an arrays data structure with one entry per segment, the hardware would be doing something like this to obtain the physical address. So this is the code that the hardware will gonna actually use to implement that from one CPU base and bound pair to segment registers with code, heap, and stack. So first, get top 2 bits of 14-bit VA. Segment equals to virtual address and segmask. Then double greater than segship. Now get offset. Offset equals to virtual address and offset mask. If offset is greater than or equal bounds or segment, raise exception, protection fault. Else, physical address equals to base segment plus offset. So that's the physical address, and then register equals to access memory physical address. So in our running example, we can fill in values for the constant above. Specifically, segmask would be set to 0x3000, segship to 12, and offset mask to OXFF. So you may also have noticed that when we use the top 2 bits and we only have 3 segments, code, heap, and stack, one segment of the address space goes unused. So there's still one segment of the address space that unused. To fully utilize the virtual address space and avoid an unused segment, some systems put code in the same segment as the heap and thus use only one bit to select which segment to use. So some system actually put code as the same segment as the heap, therefore only use one bit to select which segment of the code to use instead of 2 bits. So another issue with using the top so many bits to select segment is that it limits use of the virtual address space. Again, another issue with the using the top so many bits to select a segment is that it limits the use of virtual address space. So there's an weakness on using this top so many bits is that it limits the use of virtual address space. Specifically, each segment is limited to a maximum size, which is in our example is 4 kilobytes. Using the 2 bits to choose segment implies the 16 kilobyte address space get chopped into 4 pieces or 4 kilobytes in this example. If a running program wishes to grow a segment, say the heap or the stack, beyond the maximum, the program is out of luck. So there are other ways for the hardware to determine which segment a particular address is in. In the implicit approach, the hardware determines the segment by noticing how the address was formed. If, for example, the address was generated from the program counter, it was an instruction fetch. So that's the hardware way of automatically noticing what kind of code is that. If it is generated from program counter, it is an instruction fetch. Then the address is within the code segment. So it means that comes from the code segment. If the address is based off the stack or base pointer, it must be in the stack segment. So remember the pointer with int asterisk x we have, it means that from the stack segment. And other address must be in the heap. What about the stack? So thus far we have dealt we've left one important component of the address space, the stack. So we discussed how to determine the hardware determine the code and the heap. But how about the stack? The stack has been relocated to physical address 28 kilobytes in the diagram above, but with one critical difference. It grows backwards towards lower addresses. So instead of growing upward, it grows backwards towards lower addresses. In physical memory, it starts 28 kilobyte and grows back to 26 kilobytes. So how do we find that address? So that 26 kilobyte corresponding to virtual address 16 kilobytes to 14 kilobytes translation must proceed differently. So this is how it looks like in the process. Here 16 to 14 kilobytes since it's moved backwards, but in the process it's look upward, right? So here the first thing we need is a little extra hardware support again. So again, hardware support. Instead of just base and bound values, the hardware also needs to know which way the segment grows. A bit, for example, that is set to 1 when the segment grows in that position direction and 0 for negative. So we will determine if it a 1. So for 1, it means it grows positive. For 0, it means it grows negative. So that's how the hardware will help us. So if it returns 1, it means it grows positive, and 0, it means it grows negative. Therefore, we are talking about the backward, which is the stock. So our updated view of what the hardware tracks is seen in figure 16.4. So it's here. Code heap 1 1 and then stock is 0. So segment registers with negative growth support. So with the hardware understanding that segments can grow in negative direction, the hardware must now translate such virtual address slightly differently. So it will now translate the virtual address just like in the representation before. After the loaded fetch or the fetch instruction, it translates the virtual address. It will now translate that a bit differently. Let's take an example stock virtual address and translate it to understand the process. In this example, assume we wish to access virtual address 15 kilobytes, which should map to physical address 27 kilobytes. So that 15 kilobytes, just like before, it is mapped to an actual physical 27 kilobytes. Our virtual address in binary form does look like this: 111100000000, which is equivalent to hex 0x3C00. So the hardware uses the top two bits 11 to designate the segment. So from 0001 now 11 to designate the segment for stock, but then we are left with an offset of 3 kilobytes. To obtain the correct negative offset, we must subtract the maximum segment size of 3 kilobytes. In this example, a segment can be 4 kilobytes, and thus the correct negative offset is 3 kilobytes minus 4 kilobytes, which is negative 1 kilobytes. So that's how we find the stock. So we simply add the negative offset, negative 1 kilobyte, to the base 28 kilobytes to arrive at the correct physical address, which is 27 kilobytes. So the bounce check can be calculated by ensuring the absolute value of the negative offset is less than or equal to the segment's current size, in this case 2 kilobytes. So the bounds are checked using the size again. That make sure that it used less than or equal inside the code to check if it's still inbound. So that's basically how it does that. So in this example, a segment can be 4 kilobytes. So where's the 4 kilobyte here? In the program code, for example, we minus that, right, the stock. So let's not worry, that's not that important. We already understood it. So although we say for simplicity that the stock starts at 28 kilobytes, this value is actually the byte just below the location of the backward growing region. So the first valid byte is actually 20 kilobyte minus 1. So though the 28 kilobytes is the last size in the process or the physical memory, the first actually valid byte or the first one is the 28 minus 1, which is the set 27. So in contrast, forward growing region start at the address of the first byte of the segment. So it started at the first byte, which is the normal way. So we take this approach because it makes the math to compute the physical address straightforward. The physical address is just the base plus the negative offset for the stack. So that's the simply about it. Base address plus the negative offset. So support for sharing. As support for segmentation grew, system designers soon realized that they could realize new types of efficiencies with a little more hardware support. Specifically, to save memory, sometimes it's useful to share certain memory segment between address spaces. In particular, code sharing is common and still in use in system today. So again, as support for segmentation grew, system designers soon realized that they could realize new type of efficiencies with a little more hardware support from that segmentation. Specifically, to save memory, sometimes it's useful to share certain memory segments between address spaces. So for that memory segments, let's say you want other code to only read on it but not write, you may be able to do that with other processes or with other address spaces. In particular, code sharing is common and still in use in systems today. So it's still in use. So though this is the early memory, virtual memory form, those types of techniques are still used today, where you have this code that could be read by other process but not execute. So to support sharing, we need a little extra support from the hardware in the form of protection bits. So basic support adds a few bits per segments. So again, since the hardware started with helping us with the first two bits 0001 11 and the offset, now to implement this, like the read only execute from other address space and process, it will basic support adds a few bits per segment. So it will add a few bits per segment, indicating whether or not a program can read or write a segment. So that will indicate whether a program can read or write a segment, or perhaps execute code that lies within the segment. By setting a code segment to read only, the same code can be shared across multiple processes without worry of harming isolation, while each process still thinks that it's accessing its own private memory. So it again hidden the memory virtualization. So the OS secretly sharing memory which cannot be modified by the process, and thus illusion is preserved. So an example of additional information tracked by the hardware and OS is shown in figure 16.5. As you can see, the code segment is set to read and execute. So the code can be read and execute. And the same physical segment in memory could be mapped into multiple virtual address space. So those same code segment or virtual address could be mapped in multiple address spaces. So here code 0032K read and execute, grow positive 1, and then heap grow positive 1, stock 0. So for stock we have read and write, heap read and write, while code read and execute. So you cannot write into code. So with protection bits, the hardware algorithm described earlier, like check if else and the offset, would also have to change. So in addition to checking whether a virtual address is within bounds, such as the if else statement that check after we convert the virtual address and execute the fetch instruction, the hardware also has to check whether a particular address access is permissible, such as the protection, whether it can read or execute. So that's another logic that must be added on that algorithm. So if a user process tries to write to a read-only segment or execute from a non-executable segment, the hardware should raise an exemption. So that's another if-else, and thus left the OS with the offending process. So fine grain versus coarse grain segmentation. Most of our examples thus far have focused on systems with just a few segments, like code, stack, heap. We can think of this segmentation as coarse grain. So as it chops up the address space into a relatively large coarse chunks. Again, most of our examples thus far have focused on systems with just few segments like code, stack, and heap. How about we add another segments? Because most of the complex processes have other segments as well. We can think of this segmentation as coarse grained as it chops up the address space into relatively large coarse chunks. So we can think of this as a coarse grain. However, some early systems like Multics were more flexible and allow for address spaces to consist of large number of smaller segments referred to as fine grain segmentation. So for the code, stack, and heap, those are limited segments, so we call that coarse grain. But for fine grain segments, we have more segments in that address space. Therefore, that's called fine grain, and it is used in an early system like Multics. Supporting many segments requires even further hardware support. So supporting many segments requires even further hardware support, not just that 0, 1, 1, 1 and additional if-else logic for the memory protection. With a segment table of some kind stored in memory. So there must be a segment table of some kind that's stored in memory to accommodate these fine-grained segments. Such segment table usually support the creation of a very large number of segments and thus enable a system to use segments in more flexible ways. So those tables support the creation of a very large number of segments and thus enables system to use segments in more flexible ways than we have thus far discussed. For example, early machines like Boros had support for thousands of segments and expected a compiler to chop code and data into segregate segments which the OS and hardware would then support. So the thinking at that time was that by having fine-grained segments, the OS could better learn about which segments are in use and which are not, and thus utilize main memory more efficiently. So that's the thinking for this fine-grained support before. That's why it was invented, because it is thought of as way to save memory. So OS support should now have a basic idea as to how segmentation works. Pieces of the address space are relocated into physical memory as the system runs. So these pieces of the address space, like the 0001, are relocated into physical address using the offset and the if-else of the hardware. And thus, huge savings of physical memory is achieved. So sometimes protection are added as well, and more complex fine-grain, right, to be able to share read-only code. Is achieved relative to our simpler approach with just a single base or bounds pair for the entire address space. Specifically, all the unused space between the stack and the heap need not be located in physical memory, allowing us to fit So specifically, all the unused space between the stack and the heap that are allocated before need not be allocated in physical memory. So it doesn't need to be allocated in physical memory, allowing us to fit more address spaces into physical memory and support a large sparse virtual address space per process. However, segmentation raises a number of new issues for the operating system. The first is an old one. What should the OS do on context switch? You should have a good guess by now. The segment registers must save and restores uh, base and bound, right? So that's clearly each process has its own virtual address space, and the OS must make sure to set up these registers correctly before letting the process again. So that's one of the issue. The OS must save those before running it again. So that's segmentation is one of the issue, which is the context switch. So the second is OS interaction. When segments grows or perhaps shrink. So what if the segment grows and shrink? How does it interact with the OS? For example, a program may call malloc to allocate an object. In some cases, the existing heap will be able to service the request because that's available in the heap memory, and thus malloc will find free space for the object and return pointer to the caller. In other cases, however, the heap segment itself may need to grow. So in this case, the memory allocation library will perform a system call to grow the heap, like the traditional Unix SBRK system call. The OS will then usually provide more space, updating the segment size registers to the new bigger size and informing the library of success. The library can then allocate space for the new object and return successfully to the calling program. Do note the OS could reject the request if no more physical memory is available, or if it decides the calling process has already too much. So that's another issue with segmentation, is if you're growing a space like a heap. So the last and perhaps most important issue is managing free space in physical memory. When a new address is created, the OS has to be able to find space in physical memory for each segments. Previously, we assumed that each address space was the same size, and thus physical memory could be thought of as a bunch of slots where process would fit in. So that's the basis of that 0001 bits and if else. Now, we have a number, that's the previous chapter. Now we have a number of segments per process, and each segment may be a different size. So previously, when we're not talking about segment, we have this fixed size, but with this segment, it could have different size. So that's the last and important issue, which is managing the space for those. The general problem arises is that physical memory quickly becomes full of little holes of free space, making it difficult to allocate new segments or to grow existing ones. We call this problem external fragmentation. So C16.6. So in this example, a process comes along and wishes to allocate 20 kilobytes. So this is the issue of free space. External fragmentation, like when in this case, like it still have overall a 20 kilobytes, but it doesn't have that contiguous, right? In that example, there's 24 kilobytes free, but not in one contiguous segment, rather in 3 non-contiguous chunks. Thus, the OS cannot satisfy the 20 kilobytes request. Similar problems could occur when a request to grow a segment arrives. So just like a heap, growing a heap. If the next so many bytes of physical address are not available, the OS will have to reject the request, even though there may be free bytes available elsewhere in physical memory. So we solved that memory not allocated inside the process. But the contiguousness, like when requesting a heap or managing this free space, are still an issue. So that's actually the second issue we discussed earlier. So aside from context switch. So one solution to this problem would be to compact physical memory by rearranging the existing segments. For example, the OS could stop whichever processes are running, copy the data to one contiguous region of memory, change their segment register values to point to the new physical location. So one way to accommodate this when it's out of bound in a contiguous is to stop one process and then copy that process and then point to a new um, address in memory, or point to the new physical location, and thus have large free extent of memory with which to work. By doing so, the OS enables the new allocation request to succeed. Though there's a workaround. However, it's not that it cannot, allocate if the contiguous space is not available. However, compaction is expensive as copying segments is memory intensive and generally use fair amount of processor time. However, doing that is actually expensive and memory expensive and use a lot of processor time. Compaction also ironically makes requests to grow existing segments hard to serve. So again, compaction also ironically makes requests to grow existing segments hard to serve. So this compaction actually does not or make the request for growing a heap, for example, or segment hard to serve and may thus cause further rearrangement to accommodate such requests. Though there's a workaround, you need like a rearrangement to satisfy that request. So a simpler approach might be to use a free list management algorithm that tries to keep large extents of memory available for allocation. So a free list that allows you to keep some huge allocation or contiguous that will always allows you to have an available space for that huge contiguous request. So there are literally hundreds of approaches that people have taken, including classic algorithms like BestFit, which keeps a list of free spaces and returns the one closest in size. That satisfies the desired allocation to the requester. So we will discuss these algorithms in the future video. So this BestFit will track all available free spaces. It keeps that list and then returns the one closest that satisfy the request. Worst fit, first fit, and more complex schemes like the body algorithm we will discuss in the future video. So an excellent survey by Wilson is a good place to start if you want to learn more about such algorithms, or you can wait until we cover some basic in later chapter. Unfortunately though, no matter how smart the algorithm, external fragmentation will still exist, so a good algorithm attempts to minimize it. A segmentation solves a number of problems and helps us build more effective virtualization of memory. Beyond just dynamic relocation, segmentation can better support sparse address space. So beyond just dynamic relocation, which is the first form of virtual memory segmentation, along with this algorithm, we will discuss in the future video, could better support address space and attempt to minimize the external fragmentation by avoiding the huge potential waste of memory between logical segment of the address space. It also fast, as doing arithmetic segmentation requires is easy and well suited to hardware. So it's also fast, as you can see how the hardware translate the offset using 0, 1 and 0, 0 and 0, 1, and the protection using a simple if-else statement. So the overheads of translation are minimal. So that overheads of that translation is minimal. That's why it was, our operating system, our CPU are able to do that. It just also needs to register that illegal access handler in the trap table. So a fringe benefit arises to code sharing. If code is placed within a separate segment, Such segment could potentially be shared across multiple running programs. However, as we learned, allocating variable size segments in memory leads to some problems that we'd like to overcome. So again, as we learned, allocating variable size segments in memory leads to some problems that we also like to overcome. So the first, like the fine grain, right? As discussed above, it's external fragmentation. There's also external fragmentation for that fine grain. So because segments are variable size, free memory gets chopped up into odd size pieces, and thus satisfying a memory allocation request can be difficult. When one can try to use smart algorithms, like the best fit, sorry, not it's like the best fit, it's like one form of algorithm like a best fit and worst fit, etc., or periodically compact memory, but the problem is fundamental and hard to avoid. So this external fragmentation is fundamental and hard to avoid. The second and more important problem is that segmentation still isn't flexible enough to support our fully generalized sparse address space. For example, if we have a large but sparsely used heap all in one logical segment, the entire heap must still reside in memory in order to be accessed. In other words, if our model of how the address space is being used doesn't exactly match how the underlying segmentation has been designed to support it, segmentation doesn't work very well. Thus, we need to find some solutions. So, ready to find them? We're gonna discuss that in the future videos. So, those are the algorithms. So, yeah, we will discuss that moving forward.